Here we have a question on implicit differentiation from winter 2019. So part A. So we have this curve given by the equation y cosine of 2x is equal to y cubed plus b, where b is a constant. The curve goes through the point 0, 2, and we wish to find b here. So we know the curve is going through 0, 2, so this is really x-y pair. So when x is 0 and y is 2, we know this equation is satisfied. So let's try plugging it in. So when x is 0 and y is 2, we get this side becomes 2 times cosine of 0, and the right-hand side becomes 2 cubed plus b, or 8 plus b. Cosine of 0, hopefully you know this, is 1. So we get 2 is equal to 8 plus b. That's telling us that b must be negative 6. So we get negative 6 for part 1. Moving on, let's go to part 2. For the curve C, find the formula for dy dx in terms of x and y. And to earn credit, we must compute this by hand and show every step of the work. Okay, so let's see what the equation was just one more time. So we have this y cosine 2x. So let me just rewrite this. Y cosine 2x is y cubed plus b, and here b just happened to be negative 6, so I'll just write negative 6. So let's try finding dy dx. Well, how you do this, if you remember implicit differentiation, is you start by taking d dx, so you differentiate with respect to x of both sides. And let's see what happens to the left side and the right side. So the left-hand side, we have a product of two things, y and cosine of 2x, so we can use the product rule. We can start by differentiating the one on the left. So when I differentiate y with respect to x, that really just by definition gets us dy dx. So that's the slope of y with respect to x variable. And by product rule, we copy cosine of 2x. Then we do plus the first thing, which is just y, times the derivative of the second thing, which is derivative of cosine of 2x. Here you have to use the chain rule. And our inside function here, is 2x. So we want to start by differentiating cosine of something. So cosine of something, when I differentiate it, gets us negative sine of something. Here, that something is 2x. So you make sure you put 2x here. And then by the chain rule, I have to differentiate something, the inside function, and then multiply by that. When I differentiate 2x, I get 2. So this is what we get. And now we differentiate the right-hand side with respect to x. So y cubed, and this is a confusing thing for a lot of people. If I want to differentiate with respect to y of y cubed, then this is 3y squared as usual. So if the variable here matches the variable that we're differentiating with respect to, then this is just the usual power rule where I just get 3y squared. But here the problem is we're not differentiating with respect to the same variable, but we're differentiating with respect to x. So we actually have to change it a little bit. And how we do it is we in fact use the chain rule. So we think of y as being our inside function. So think of this y as being something, and we have something cubed. When I differentiate something cubed, I want to get 3 times something squared. Here something is y. But by chain rule, now we have to differentiate your something, the inside function, with respect to x. So when I differentiate y with respect to x, that just by definition gets us dy dx. So I multiply by that, by chain rule. And then finally, I differentiate minus 6. Minus 6 is a constant. It's just a number, so that goes away. So we get this equation. And now we want to find dy dx in terms of x and y. And how we do this is as follows. This looks complicated, but really it's just algebra 1 process. So here we see dy dx. Here we see dy dx. And any term with dy dx will move to one side, let's say the left-hand side, and any term without dy dx will move it over to the other side. So what happens is something like this. I move this to the left side, so I'll copy this. So I have dy dx, cosine of 2x, and then I have a minus 3y squared dy dx. And then I'll move this over to the other side. Here we have a minus sign, so when I move it to the other side, I get plus sign. So we have y times sine of 2x times 2. I'll just put times 2 up front. So this is what you get. Continuing on from this, since now we have dy dx all on one side, what we can do is we can factor out dy dx. So when I factor out dy dx, I have cosine of 2x here, and I have minus 3y squared. The right-hand side stays the same, 2y sine 2x. And once I have dy dx times something is something, then I can divide by this to both sides to find the dy dx. So our final answer is that dy dx is 2y sine of 2x, and then I'm dividing by this entire thing. So cosine of 2x minus 3y squared. Before we move on, let me quickly point out one other problem type that they might ask you. So another common question is to ask you to find the equation of tangent line to the curve at 0, 2. If you have a question like this, how do you approach it? So let me quickly go over this really quickly. Well, remember what kind of information you need when you want to find the equation of the line. Well, you need a point and you really need a slope. If you have these two information, that really determines the line completely. So what is the point? Well, point they literally tell you. So point is 0, 2. And let's say we also want to find the slope. Well, slope is a dy dx, and we know expression for dy dx. But here, now let me actually mention one thing. If they phrase the problem in a way that maybe part two of this problem was not this, but you just had to find the equation of tangent line, then obviously you do have to do some implicit differentiation, like in the sense that if you don't even take d dx, if you don't even differentiate with respect to x to both sides to get this, then obviously you're not gonna get the slope. But once you arrive at this equation, there's really no need in like moving all terms with dy dx to one side, factoring out dy dx, and then solving for dy dx. There's really no point in going through all of this if all you need is to find the equation of tangent line, because you can really stop here at this point and then find the dy dx. What do I mean? Well, you know this is x and this is y, so you can just plug in x equals to 0 and y equals to 2 into this equation, and let's see what happens when we do so. So when I plug in 0, 2, we get dy dx times cosine of 2x. Cosine of 2x, well, you're taking cosine of 0, plus y is 2, times minus sine of 2x times 2. Well, here x is 0, so we get sine of 0. Sine of 0 is 0, so this entire thing actually goes away. So let me just not write it. And we know this is equal to 3y squared dy dx. So y is 2, so 3y squared is 3 times 4, that's 12 dy dx. Hopefully you know cosine of 0 is 1. So this is telling us, so we got a really nice equation in fact. This is telling us that 11 times the dy dx, when I just move this over to the other side, is 0. So we get dy dx as 12 times dy dx, or 11 times dy dx is 0. So that's telling us that slope, which is dy dx, is actually 0 at this point. So we get slope of 0. I mean, in general, you might get a different slope, but my point is, if all you want is just finding dy dx at this point, there is really no need in actually solving for dy dx, getting this, and then plugging it into this. You can just stop after this step and plug it in right away, and that's probably good enough. Anyway, so once you find the point and the slope, what you can do is, you just find the equation of the line. Generally, this is going to be not 0. Here it's pretty easy because slope is 0. But in general, what you want to do is you want to say y is equal to the slope, which here happens to be 0, times x minus the point, which is 0, x coordinate, plus this, plus 2. So in this case, of course, you get just the horizontal line y equals to 2. But in general, you might have this thing is non-zero or this thing is non-zero. You just have to substitute in the right things. Anyway, there was just a digression in case you had to find the equation of tangent line. Let's move on to final part. So here we really have a different curve r, so it's not the same one. Also passing through 0, 1, I guess. And it satisfies that dy dx is 2x minus y over x minus 2y. One of the following is the graph of r, and we want to find which one it's coming from. So this may look really tricky, but it's not as bad as in my sim. So here's one way that's guaranteed to work. Like I guess one way is for you to pick really any point. So this is not the smart way of doing it, but if you just want to get the answer in a reliable way, I guess one thing you can do is to really pick just any point on this curve. So maybe like you can look at this point, which looks like 0.5, comma, maybe like negative 0.6. So you just like eyeball it. And then you can try drawing the line, or the tangent line to this point. And it looks like this line is around the slope. Again, I guess you kind of have to eyeball based on this. I mean, maybe the slope like 0.8. I'm not sure, but this is not the way we're going to do it. But one feasible way that I learned from someone else is you can just pick a point and then you can find the slope and then you can try plugging it into this equation. Like for example, dy dx here is the slope, and your x and y are 0.5 and negative 0.6. So you try plugging it in 0.5, negative 0.6 into x and y. And then you see if the slope is actually 0.8. If the slope is not 0.8, then you know it's not 2 because at this point we better have slope of 0.8, but the equation is telling us that it's not. So that's one way. You can just try picking bunch of points and see if it's consistent with this equation. You can try something similar for other equations and go that route. I mean, that's gonna work. I mean, that's guaranteed to work. If you just try it out on enough points for all 4 graphs, you can count out 3 of them. But maybe a more efficient way of approaching it is as follows. Like, for example, if I take a look, so if you take a look, I'm trying to see if there's some easy point. So maybe let's take a look at here. So this point is really easy in the sense that the line is horizontal. So we know this has a slope of 0, and the point here is 0, 1. So we know at 0, 1 you better have slope 0, and that's a bit easier to check than slope of like 0.8, or where you have to eyeball the slope. So here it's not too bad. So x is 0, y is 1. So when x is 0, these disappear. When y is 1, we get negative 1 here, negative 2 here. When you divide, dy dx is not 0, right? So when I plug in x equals to 0 and y equals to 1 here, you don't get 0 as the output. So that's already telling you that it cannot be 3. So you can discount 3. And another place you can look at is where slope is infinite. So like, for example, here we see that we have a vertical tangent line. So here the slope is infinite. Another way of thinking about it is that slope is undefined, because I mean you have an infinite slope in some sense, it's vertical. So you know at 1, 0, if 4 is the answer, then we better have an undefined slope. Well, how can dy dx be undefined? Well, a fraction is undefined when you're dividing by 0 here. So all we have to check, for example, is at 1, 0, are you dividing by 0? So the slope is undefined. So let's check this. So at 1, 0, well, x is 1, 2y is 0. Well, the bottom is not 0. You're not dividing by 0. So this is actually defined. So you know it can't be 4 either. So using reasonings like this, now maybe you can check it at this point or this point, or maybe here you have a horizontal line, here you have a vertical line. So by checking more points like this, that's guaranteed to work. That's probably more efficient than picking a random point. So focus on where you have a horizontal tangent line or vertical tangent line. But actually something that one student pointed out to me, which I think is the fastest way of getting this, is as follows. When y is 0, then this thing just becomes 2x over x because y is 0, and we get 2. So what that's telling us is that if I look at any point on the curve on the x-axis, remember the x-axis is when y is 0, we better have slope of 2. Right? Because on the x-axis y is 0, and this equation is telling us that dy dx is 2. But if we look at, for example, curve 1, we see that here we have an infinite slope, so it's not slope of 2, so it can't be 1 either. So we know it's not 1. And this actually in this particular problem happens to rule out everything, right? Because here we have an infinite slope on the x-axis, so it can't be 3. Here we have an infinite slope on the x-axis, so it can't be 4. Whereas if you look at 2, it does look like you have a slope of 2 if I look at the points on the x-axis. So that's another way of doing it. You can consider y equals to 0, see what slope you must have if you have a point on the x-axis. You can also try x equals to 0 and see what slope you have to have if you're on the y-axis. So that's another strategy you can use. Anyway, the answer to this question is 2.